In Newtonian gravity, we know that some quantities are conserved, like the total energy E and the angular momentum vector L. It turns out there is an extra one known as Laplace-Hungelen's vector A, or LRL for short. Here is the expression for the LRL vector, and there are three things we want to know. 1. Why is it conserved? 2. Where does it come from? And 3. What does it physically represent? If we only focus on the first question, like a lot of textbooks do, we can perform a bunch of calculations to see that this quantity is conserved, but that's not very interesting. What's interesting is to see where this expression comes from. Historically, there were many ways to derive this because the LRL vector was rediscovered so many times from different people doing different things. For this video, we will also rediscover the LRL vector, but using a method first documented in 2008. Along the way, we will also answer the other questions. It starts with a more general setup. A particle is moving in some potential. In the case of gravity, it is negative gmm over distance from the origin. The equation of motion has the basic form of F equals ma, where the force is given by the negative gradient of the potential V. For some potential, this equation can be difficult, maybe even impossible to solve. It would be nice if you can somehow transform the equation so that we are dealing with a different potential that might be easier to work with. These equations will be related by conformal transformations, and the two potentials that can be transformed into each other are called duals. This might sound familiar to those who watched the previous video, but I'm using a different, much more general method here, which uses something called Maupertuis principle. The goal of the principle is to find the trajectory of the particle, but we don't care how it actually moves along it. As far as Maupertuis is concerned, the particle could have moved erratically like this. In other words, this principle determines where the position q can be, but not necessarily the time evolution, or q as a function of time. To explain the details, we need the action principle, or more precisely, the Hamiltonian version of it, which is the superior version. The backdrop of this version is something called the extended phase space, where we need the position q, momentum p, and time t to describe the particle's state. The state carves a trajectory gamma in this extended phase space, and the action principle is that a certain line integral along this path gamma, known as the action S, is extremized. I want to clarify what extremize means, as it's relevant later on. When I vary the path slightly from gamma to gamma prime with the two endpoints fixed, I can compute the difference between the s's along the different paths. Extremize here means this difference is 0 to first order for all infinitesimal variations gamma prime. The action principle is that, in this case, gamma is a physical path that a particle's state can take. For more details, I've previously made a video on this. Now let's focus on the details of S, in particular, this H known as the Hamiltonian. It encodes the physical system, but it's also just a function of Q and P, so we can compute H at any point and S along any path we like. In the cases we are interested in, H is the total energy. The first term is the kinetic energy, the second is the potential energy. Conservation of energy means that H is constant along physical paths that a state can take. So if gamma is a physical path, then H is constant along there, but any variation of gamma might destroy the constancy of H. The action principle states the equivalence of two statements, but let's concentrate on one direction. When gamma is a physical path, delta S equals 0 when we choose to only compare with a specific subset of variations gamma prime where h is constant. For those paths, h can be put outside the integrand, leaving us with h times the integral of dt, which is just h times the time elapsed along the path. Since we are comparing against paths that also have the same endpoints, delta t is the same across all variations gamma prime. So the difference in S is the same as the difference in just this p dq integral. This integral is known as the abbreviated action, denoted as S0. We can then replace this statement with delta S equals 0 by delta S0 equals 0. So if gamma is a physical path, then this S0 is extremized among the curves that have constant h. But now the abbreviated action doesn't depend on time, so I can project all paths to the QP plane and this S0 doesn't change. So we can apply this statement purely on the QP plane. In other words, if gamma is a physical path on the QP plane, then delta S0 equals 0 among paths on this plane that have the same endpoints and constant h. Turns out the other way is true as well, but it's a bit trickier to show. This statement is what I'll call the Hamiltonian version of Maupertuis' principle. I've only illustrated one dimension of Q and one dimension of P for us to visualize, but you can generalize to higher dimensions with vector P dot dq. Now we go one step further. Let's say we have 2 dimensions of Q and 2 dimensions of P. For a physical path, if we know how it moves in the Q space, then we should be able to use momentum P equal to m times dq by dt to ascertain the path in the P space as well. The only trouble is if we only have this curve in Q space, we don't know how Q evolves in time, let alone the velocity. We still know that P is pointing along the tangent though, so we know the direction of P. The magnitude can be found with conservation of energy. Previously, we are comparing against variations gamma prime that do not necessarily obey that, they only need to have constant h. So, S0 is extremized among a wide class of paths, and hence also among a narrower class of gamma prime where P also equals m times dq by dt. Turns out the other direction is true as well. With this, we can do everything in Q space because these relations between Q and P allow us to express everything in terms of Q. This is what I'll call the Lagrangian version of Maupertuis' principle. Let's unpack what this means. Since P equals m times dq by dt, it is tangent to the curve and parallel to dq. The dot product gives the length of P times length of dq. Now we impose conservation of energy, so the length of P squared over 2m plus potential energy is a constant E, allowing us to express the length of P in terms of Q and E. The abbreviated action is then the integral of this times the length of dq. Now that the integrand is fully in terms of Q, we can replace this statement by just considering the variations with the same endpoints in Q space. This is how we can determine the trajectory in Q space. Let's bring Newtonian gravity back into the picture. Since the orbits will be on a plane, we can reduce this problem to a 2D one effectively and use this statement on a 2-dimensional Q space. But a 2D plane can also be viewed as a complex plane. Any point AB can be thought of as the complex number A plus BI, and any vector with components AB can also be thought of A plus BI. We can then rewrite everything using the language of complex number z. For gravity, this potential v is negative gmm over distance from origin, or negative gmm over the modulus of z. But for now, let's keep the potential general. I guess we should also call this the z-plane now that we have changed everything to z. In this language, a physical path on this z-plane is one that extremizes this abbreviated action S0. What follows is a pretty genius trick. The idea is to transform the complex plane with a complex function f. F can be anything you like, and this transformation gives another curve f of gamma on the transformed plane, which we now call the w-plane. We want this f of gamma to represent a physical trajectory with possibly different energy and different potential. In other words, we hope this path extremizes a new S0 with new energy E tilde and new potential V tilde. Since gamma extremizes the old S0, f of gamma should extremize the same abbreviated action with all the z's replaced by f inverse of z. So f of gamma simultaneously extremizes these two integrals. I want to emphasize that the integral on top is definitely extremized based on the fact that gamma was originally physical, but the other integral is kind of a wish list where we hope there is an E tilde and a V tilde such that f of gamma extremizes this integral as well. If it turns out that they only differ by a constant factor, then f of gamma will extremize both integrals at the same time. So the strategy is to start from this integral on the left and then massage it to look like some constant times the integral on the right. The first thing to unpack is this df inverse of z, which has this derivative by the inverse function rule. Next, we push this clunky factor into the square root, making each term multiply by this factor squared. Finally, we set this bit to be the new energy E tilde and the other bit to be negative of the new potential V tilde, and we have successfully massaged the form we wanted. We've written everything in terms of z, but z is a dummy variable and is integrated over, so the two integrals are the same. But E tilde has to be a constant. That's why I didn't choose E tilde and V tilde the other way. Both E and E tilde being constant forces f prime to also be a constant. Sure, you can do that, but f will just be scaling and isn't useful to transform to something easier. In the literature, there is a final step since it's weird that we need a completely new potential for slightly different e's. So we pull out a factor of square root of e or square root of minus e depending on whether e is positive or negative. In Newtonian gravity, if the orbit is bounded, we expect the total energy E to be negative, so we focus on the case with negative E. Like before, we choose this to be E tilde and the other to be negative V tilde. This differs from the form we wanted, but it's fine as it's only a constant factor difference, and delta of one s not being 0 means delta of the other is also 0. With this identification of E tilde and V tilde, we can find the f that makes all these work. Denoting u as f inverse of z and rearranging it a bit, we have v of u equals E tilde modulus of f prime of u squared. For gravity, we substitute in the form of v, so the modulus of f prime is proportional to 1 over the square root of modulus of u. Because of this, let's set f prime to be 1 over 2 square root of u. The reason I set the proportionality constant to a half is that when we integrate it to find f, it's just square root. This choice determines the new energy E tilde in terms of the old one. Next, we turn to the other term that we chose to be negative V tilde. We just need to differentiate f to find V tilde in terms of u. Finally, since u is f inverse of z and f is the square root function, u equals z squared, and hence the new potential is 4 times the modulus of z squared. Let's take a step back and see what we have done so far. Originally, we had a physical trajectory gamma on the z-plane with total energy E and potential inversely proportional to the modulus of z. We've shown that when we apply f, which in our case is the square root function, the new f of gamma will also be a physical trajectory, but with new energy and new potential proportional to modulus squared. In other words, we have transformed Newtonian gravity into a harmonic oscillator. The harmonic oscillator is much simpler to deal with, so it's great that we can equate gravity to this. Any conserved quantity for the harmonic oscillator should then correspond to some conserved quantity in gravity. In particular, one of them corresponds to the LRL vector. But what is this elusive quantity for the harmonic oscillator? The idea is to use the equation of motion. The potential is 4 times modulus squared, and the force is the negative gradient of this, which is negative 8w. Importantly, we don't have to use modulus to represent the force. This is really different from other potentials. If the potential was something else like gravity, then the force will involve modulus cubed, with the w in the numerator indicating the direction of this force. The absence of modulus in the equation means that purely algebraically, this equation is the same as that of a 1D harmonic oscillator. Therefore, with the same algebra, this quantity, which would have been the energy for the 1D oscillator, is conserved. The real energy of this 2D harmonic oscillator is negative 4 gmm over E, and the conserved quantity we just derived is sort of the complexified version of energy. We now need to represent this complexified energy in terms of the original variable z. We denote this as EC, C for complexified. Since w is the square root of z, we can immediately replace this w squared as z. The difficult bit is the velocity of w, but we can calculate its direction and magnitude separately. Suppose the original velocity on the z-plane is v, a complex number to encode the direction. This v is the time derivative of the position z, and the w dot we wanted to calculate is also a time derivative, but in principle, the two times can be different since the Maupertuis principle that we use to deduce the square root relations only cares about the trajectory itself but not the time evolution, so you can only know the direction of the movement but not the speed, at least not directly. Nevertheless, we can differentiate w with the help of chain rule. Since w equals square root of z, dw by dt is 1 over 2 square root of z times dz by dt. But now since dz by dt is v, we can write w dot as shown on screen. One thing to note is that everything in the bracket is real since t and tau are real, so this part doesn't influence the direction. The remaining bit, v over square root of z, controls the direction. For future convenience, we make this a unit vector, so we divide this complex number by its modulus. Next, the magnitude of W dot. This can be obtained by the real energy, but we don't explicitly compute it yet. Whatever it is, we can write W dot as its magnitude times the unit vector that indicates the direction. Squaring and multiplying by m/2, we obtain this expression. We can substitute this back into the expression for EC. As a reminder, W equals square root of z, so the other bit just gives z. The first term can be rewritten as the real total energy minus 4 times the modulus of W squared. Just like how we replaced W squared as z, we replace mod of W squared as modulus of z. Next, we are pulling out a factor of 4 over me because the remaining bit is precisely the LRL vector. So a preliminary interpretation of the LRL vector is MEEC over 4, where E is the total energy for gravity and EC is the complexified energy for the corresponding harmonic oscillator. 2 questions left to answer. 1. How is this expression related to the usual form of the LRL vector? And 2. Is there some interpretation of EC other than the complex analog of energy? Let's focus on this form of the LRL vector. E is the total energy in gravity, which is m mod v squared over 2 minus gmm over mod z in the language of complex numbers. Concentrating on the first bracket here, we can substitute the expression for E, but we realize that 2 of the terms cancel. We can then combine this remaining term with v squared over z and mod z over mod v squared. The 2 mod v squared in the numerator and denominator cancel, and the 2 mod z in the numerator can cancel a factor of z in the denominator to give the complex conjugate of z. So the first term is simplified to negative m squared v squared z star over 2. We now deal with the second term using the expression for the energy E again. This step is pretty straightforward, and if we add back the first term as well, you might start to see some resemblance to the usual form of the LRL vector. This k is the proportionality constant for any inverse square law force. In the case of gravity, it is gmm, so these 2 terms exactly match each other, one in vector form, the other in complex number form. We just need to know why the other part matches the cross product. This time, we start from the cross product. Suppose the position r and momentum p are in this configuration. We know they both lie on the orbital plane, and the cross product points upward according to the right-hand rule. This upward vector is perpendicular to p, so when we cross p with it, the magnitude is just the product of the magnitudes of p and r cross p, and the direction is perpendicular to p on the orbital plane. In this setup, going from p to the triple product is a clockwise 90-degree rotation. In the language of complex numbers, this is mv, the complex number associated with the vector p, multiplied by negative I. We multiply by the magnitude of r cross p to match the magnitude of the vector. What remains is to express this magnitude using complex numbers. We let r and p be on the z equals 0 plane with these components. The cross product has only one non-zero component, which can be calculated with the crisscross pattern giving AD minus BC. This is also the magnitude. The corresponding complex numbers for R would be Z, which is A plus BI, and that for P is MV, which is C plus DI. A clever way to make AD minus BC is to conjugate Z and then multiply MV. You can pause and verify the calculation, but now the imaginary part is precisely AD minus BC. To properly extract this imaginary part, we can conjugate both sides and subtract one from the other. Finally, using this result, we can express the triple product in complex numbers, which is m squared v times zv star minus z star v over 2. Now compare with the complex form we previously obtained, and they do match. Let's take another step back. We deduced that taking the square root turns Kepler's problem into a harmonic oscillator, and EC, the complex analog of energy, is conserved for the harmonic oscillator. We then construct the LRL vector out of M, E, and EC, all of which are conserved. Finally, we checked that this is the same as the usual form of the LRL vector. But how do we make sense of this vector? Let's first consider the associated harmonic oscillator, which has an equation of motion relatively easy to solve. The general solution is a linear combination of two exponentials, with alpha and beta being complex constants. Generally, this amounts to an ellipse on the complex plane centered at the origin. We can directly compute EC with this solution of W, but since EC is conserved, we can just compute W and W dot at tau equals 0, which is relatively straightforward. Then, we compute EC at tau equals 0 by substituting these values of W and W dot. With a bit of work, we get 16 alpha beta. Let's put this aside and compute one more conserved quantity, the actual energy for the harmonic oscillator. Again, we only need to compute this at tau equals 0 since it's conserved. The algebra is more complicated, but in the end, a lot of terms cancel, leaving us with 8 mod alpha squared plus 8 mod beta squared. We computed the real energy because from the correspondence between gravity and harmonic oscillator, the energy for the harmonic oscillator is negative 4 gmm over E, where E is the energy for Kepler's problem. So the quantity we just computed is negative 4 gmm over E, or equivalently, E equals negative gmm over 2 mod alpha squared plus mod beta squared. Altogether, we have both EC and E in terms of alpha and beta, which are the two complex coefficients in front of the exponentials. The LRL vector, as discussed before, is MEEC over 4, and we can represent this in terms of alpha and beta. Now we are ready to put a meaning to the LRL vector. The W in the harmonic oscillator was the square root of Z in Kepler's problem, so to get Z from W, we square it back. We have the solution for W in the harmonic oscillator, and we square it to obtain Z. The first part still signifies an ellipse, but the remaining bit shows it is now centered at 2 alpha beta. The LRL vector also has this 2 alpha beta bit. What about the mod alpha squared plus mod beta squared in the denominator? For that, we compute a weird quantity mod z plus mod z minus 4 alpha beta. The first step is a pretty direct substitution, giving two similar-looking moduli, but they are now both perfect squares, so we write them as some modulus squared, and doing similar computations as before, a lot of terms cancel, and we are left with 2 mod alpha squared plus 2 mod beta squared, and this appears in the expression for the LRL vector. We previously established that the z orbits are ellipses centered at 2 alpha beta, and what we showed was that for any point z on this orbit, the sum of its distance from 0 and 4 alpha beta is always a constant, 2 mod alpha squared plus 2 mod beta squared, which not only showed that 0 and 4 alpha beta are foci, but also that 2 mod alpha squared plus 2 mod beta squared is the so-called major axis of the ellipse. Basically, when you move z to align with the two foci and consider the sum of distances, the shorter distance is double counted. But by symmetry, I can move it to the other side of the ellipse so that the sum of distances is actually the long diameter or major axis of the ellipse. Equivalently, the semi-major axis from center is mod alpha squared plus mod beta squared. So the LRL vector points in the negative 2 alpha beta direction, and since the center is at 2 alpha beta, it points from center to the origin. The magnitude is gmm squared times the distance from the center to a focus of the ellipse divided by the semi-major axis. This ratio is called the eccentricity of the ellipse, a measure of how far away it is from a circle. In the beginning, we wanted to figure out 3 things about the LRL vector. The fact that the LRL vector is MEEC over 4 in complex form solves the first 2, since energy is conserved, even the complex one for the harmonic oscillator, from the equation of motion. The LRL vector also has a relatively simple interpretation. It points along the major axis of the elliptical orbit, and the magnitude is proportional to the eccentricity. Usually, a conserved quantity comes from an underlying symmetry of the system. Conservation of energy comes from time translation symmetry, and conservation of angular momentum comes from spatial rotational symmetries. But conservation of the LRL vector doesn't come from an obvious symmetry. This video only focused on what the LRL vector is, but the next one will make this obscure symmetry more obvious. Thanks for the patrons, and don't forget to like and subscribe. See you next time!